Okay, in this talk we're going to revisit the quantum oscillator model of stock markets and talk in particular about these two properties of Q-variance and the Q distribution. Q-variance refers to the property that the expected variance of log returns x corrected for drift over a period t follows to good approximation in this formula, sigma squared plus z squared over 2, where z is equal to x divided by the square root of the period. So we discussed that in QEF15. And Q-variance again follows because we're modeling price changes as the displacement of a quantum harmonic oscillator. So now we're not going to explicitly model the market maker, we're just looking at this quantum oscillator as describing the price distribution. And if we perturb the center of the oscillator by some amount here is 0.14, then it's going to enter an oscillation, a coherent state where it just oscillates from side to side like this, and the total variance is given by the Q-variance formula. So that's where it's coming from. A corollary of Q-variance is that the price change distribution will follow a Poisson-weighted sum of normal curves, where the Poisson rate parameter is lambda equals 0.5. So this is what the formula looks like. It's so these are the Poisson weighting terms, which are given by this formula, and then we have a bunch of Gaussians with standard deviation sigma n, which are given by this formula, and we're using lambda equals 0.5. And the distribution looks like this plot, so it's composed of these different terms. This is n equals 0, n equals 1, and so you can see it's converging very quickly to this Q distribution shape. So where is this lambda 0.5 number coming from? Well, there's a number of different ways to demonstrate this. So one is to look at the individual transactions which occur over the period and look at the contributions from each of those and see how the price change distribution builds up. But another way which we're going to look at here is just to show that this Q distribution is consistent with Q variance, because obviously if you had, let's say, just purely normal distribution, it wouldn't work, because the normal distribution has a constant volatility, constant standard deviation, and therefore you're not going to get that Q variance, that quadratic relationship. Okay, so to see that, if we assume Q variance, we assume that the average variance varies in this way as a function of z, and then we kind of compute the variance over the entire distribution, we're going to get a that is the variance as a function of z, and this is the probability density as a function of z, but now we're leaving lambda an open parameter. And we can, when we use the expression for f, then we get all of this. And so we can kind of think of this as two parts. We've got a part with over here with a sigma squared and a part with a z squared over 2. And if we take the sigma squared out, that's a constant term, and then we just have a Poisson weighted sum of Gaussians, and you can just check that that's going to equal sigma squared. And then that leaves us with this other part with the z squared over 2. And for that we can use this particular relationship here, which allows us to simplify all of that in terms of, we just get a Poisson weighted sum of sigma n squared terms, and using the expression for sigma n, we're going to get this the sum works out to sigma squared times 3/2 plus lambda. So we've used a couple of relationships here, like the sum of the Poisson parameters is equal to 1 and their average is equal to lambda. Okay, so that gives us one view, but like on the other hand, the variance of the Poisson weighted distribution can be obtained directly just by taking the weighted average of the variance of each term. So that would give us this. This would give us the Poisson weighting times sigma n squared. So that's the variance of each term. And then again, using the expression for sigma n squared, we arrive at this, sigma squared times 1 plus 2 lambda. So from above, the previous page, we had sigma squared times 3 half plus lambda. Now we've got something different. We equate these, and it works out that lambda is equal to 1/2, and the total variance is 2 sigma squared. So again, sigma is this minimum volatility, which applies for small displacement. So we got this, the total variance is going to be twice sigma squared. Okay, so this Q distribution, which we're calling this thing with lambda is equal to 0.5, this is consistent with Q variance. Is it consistent with data? Well, this plot, so what we've done here is we've calculated variance as a function of Z for 355 stocks from the period going from 1992 to April 2025. So the stocks which we're considering are ones which have been in the S&P 500 index, and they have data for at least 75% of the period, so since around 2000. So if a stock has just been in for a short time, we're not using it. And we looked at periods. We're compiling all of this data over periods of 1 to 50 weeks, where we compute the volatility over each period. We bin it to get these thin black lines here, which are kind of noisy, but then when we take the mean of all of these stocks, we get the blue line, which follows this nearly perfect parabolic shape. And the red line is the quantum model with a very small shift to account for effects such as Q, very small horizontal shift. But basically, the quantum model is in excellent agreement with the mean of all of these lines. So that's Q variance. How about the Q distribution? Well, here, this plot, what we've done is we've calculated the normalized price change distribution in terms of Z for each of those 355 stocks again, and we get all these thin black lines, and the blue line is the mean. Now, in this case, in order to kind of compare like with like, some of these stocks have low volatility, some have higher volatility, so what we can do is we can normalize by dividing the price change, normalizing to a sort of their average volatility. And now we get this plot here. So blue line again is the mean. The red line is the quantum model, Q distribution, again with a very small shift to account for effects such as skew. So this is interesting. Basically, we have this all of this data, and we normalize the calculated distribution, and this is the shape that emerges. To just summarize then, the quantum oscillator model predicts that variance will show the property of Q variance, and price changes will follow this Q distribution, which is associated with that. They're connected because the Q distribution is consistent with Q variance. The predictions have been tested against stock market data and are in excellent agreement with results. However, neither Q variance nor the Q distribution are consistent with a classical random walk, and that's probably why they have not previously been used in finance. And there's a couple of references here for further reading.